Welcome everybody to the second day laboratory of the summer school for drug discovery with machine learning. I'm Cristian, thank you for the introduction, and hopefully you're having a nice stay here in Montreal and at the summer school. And we're gonna jump right into it. So today we basically went more into the machine learning side, into the structure-based drug discovery, and hopefully you had some nice talk with what we did with Giovanni Corso and Gianni and Tivari on DiffDoc, the problem with the docking that we have in the computational chemistry. Or we are actually training a new machine learning model to have better prediction of the energy and trying to substitute the force field with better accurate models, and also the problem that we have right now in enhanced sampling methods. So there's going to be a talk that is going to try to wrap a little bit together and trying to basically convince me and probably, hopefully, also you that this field needs machine learning scientists and computational chemists working together to solve this kind of a complex issue. So the agenda for today is wrong. So we are starting 30 minutes before, but basically I'm going to do the introduction, just an overview on the drug discovery process and how structure-based method actually fit into this process. We're going to have a little break, and then me and Stephan are going to show you the code and the laboratory on docking and active learning for binding free energy prediction. And hopefully then we can have a nice recap and also a nice discussion on how to progress this field further or the current limitation of the field and the methods. Okay. This is a slide that my colleague Cass actually showed yesterday, and it's a really nice slide. And we're basically showing that today we're gonna just under the structure-based method. I have only one little issue with this slide, is that it seems that if you see the diagram, is that when you start your drug discovery cycle, you're just gonna try to understand if you want to pick a ligand screening methodology or a structure-based methodology before moving to further stage in the drug discovery. Hopefully, I'm going to show you that the reality of a drug discovery process is way more complex, and ligand-based screening or ligand-based technology, machine learning methods are concatenated with the structure-based method and the structure-based machine learning methods. So as a motivation, probably you already understood that protein structure provides valuable info for us. You already heard way too many times binding free energy or binding affinity today. And the point of this talk is, can we actually predict better properties by considering also the protein structure? So instead of just building a machine learning model on a smile or on a graph, or like in this case, just a little smile of a psilocin molecule, we can have a model that predicts something from the docked structure or just the ligand binded to the PDB structure. In this case, we in the laboratory we're gonna use this protein that is the EGFR, more precisely the 6VHN, that is rendered here on from VUMD. So in the pipeline of drug discovery, there are really difficult, and the more you go further, the more time and money you need to invest. We are going to basically focus on the target identification and it to lead the lead optimization phase. That's because most likely the structure-based method and also the ligand-based methodology are going to be utilized, because on the preclinical evaluation and the clinical assessment are more experimental and conducted in different ways, where actually acquiring data is really hard. There are other different issues. So structure-based drug design on these kind of three phases are in target identification in homology modeling. So basically creating the PDB structure of your protein that you're going to try to target, or if you're not doing homology modeling and you're more into machine learning, basically AlphaFold and Rosetta Fold and all these kind of new generative models that are really powerful and they're trying to revolutionize this field. Once you have your protein structure, and so basically your target, you're basically going to try to do a hit to lead phase. So in this kind of case, you are selecting a really big data set of compounds that you're going to try to dock. So basically just forcing it into the protein and see if they stick in a decent way. And in the case they're going to be progress further down the pipeline naively. It's still a difficult step. And then you're going to do to the lead optimization. Hopefully, after the hit to lead, after a countless talk with your chemist, med chem in the company, you have a good understanding of what's the scaffold of your series, and now you're going to try to optimize from it. So basically, you're going to try to see your structure and of the protein and see how you can increase the potency, okay, while maintaining some interesting properties like solubility, lipophility, and all this kind of interesting properties that we need to do. And in this kind of step, structure-based drug design is basically a more complex docking technology. So you're basically going to have some crystallized water from a PDB that you really care about. You're gonna have probably you're enhancing the solvation of this kind of PDB, but also you're gonna run physical simulation as enhancing sampling method like energy perturbation or just molecular dynamics to have better prediction of the binding free energy. And our lab is exactly in the hit to lead optimization phase, mostly on the hit to lead, but all the talk that we're going to have can be applied on the physical simulation that you can run on the lead optimization phase. So, as I basically said 2 minutes ago, probably, ligand-based and structure-based design are hugely interconnected. So from target identification, you can basically start by screening a Campbell or another dataset to grab a lot of ligands that are that you know that are going to bind the target. And in that kind of case, you can just start doing the hit to lead by doing a shape screening. You also have the target in this kind of case, or just doing what yesterday my colleagues Lou and Cass showed. So basically, just screening with a machine learning model. But at the same time, you're not just gonna proceed further with just a ligand alone. You're gonna have a target, and you're gonna probably try to dock. You're gonna see if it's fit well, if it's gonna go further along. And if you're not doing just a ligand screening, you're gonna start from a protein, probably from a chemist that did some crystallography, a cryo-EM or an NMR or other kind of techniques. So you're gonna do both sides, the ligand base and the structure base, at the same time, most likely. Then you're going to go through the filter, so on, and you're going to be hopefully with a good candidate in the lead optimization stage, when you're going to use a more expensive simulator like molecular dynamics or other kind of physical simulation, and then it's all in the hands of experimentalist, chemist, biology that knows how this kind of stuff works in a more complex way at the really big mesoscales. Kind of worked. Yeah, perfect. So basically, for who doesn't know, docking is basically just predicting the binding pose and some kind of affinity of a molecule. I use some kind of affinity because it's a really imprecise oracle. It's not a real binding free energy or binding affinity, but it's more like a score that the programmer is telling you. So it's a tricky value to actually take in consideration. And also, a thing of docking is that it can do almost everything. It's like having an hammer. And if you have an hammer, everything is a nail. You can basically grab a really, really big molecules and just force it inside, so in some kind of way. And that's basically just for showing that the output from a docking process and also the input should be analyzed. A lot of the times PDB files have complex information inside, and just grabbing a random PDB, not cleaning, not checking what is inside, can lead to really bad results at the end of the pipeline. You can just maybe there was another crystal inside, maybe you got the wrong site, and when you're down the line of a drug discovery process, this is a lot of money that you're spending. And also, just wanted to show that molecule because just I want to remind that drug discovery is hard. That molecule that is really, really big is also a real drug. if I remember correctly, is the drug of the year of the 2023, and it's from Merck. It's just an oral inhibitor for the PCSK9 protein. So we are using a lot of small molecule here and this kind of stuff, but the macropeptides and other kind of molecules that are way bigger in size and actually break the normal screening filter are also really viable candidates. So it's a complex field. So I explained a little bit how the E2lead phase docking is done, and I just want to show a little bit how these kind of techniques can go to E2lead to it optimization. So we basically at the docking predicting some kind of affinity that is more of a score, and we want to basically have a better oracle, a better model that predicts this. So someone, probably a computational chemist, basically went back to you and asked, what if we use molecular dynamics? And we said, sure, let's do that. We ran our molecular dynamics in the pocket after did some cleaning, parameterization, or all the usual stuff of a computational chemist, and we calculate some end-to-end result with what we usually call MMPBSA, MMGBSA. So the only thing that differs that the docking is a rigid, mostly. You can also do flexible docking, but we're talking about the rigid. And in this kind of case, we are also trying to consider the flexibility during the molecular dynamics, and so a little bit of the entropy and the enthalpy in the process. And we have a better binding affinity, still not that great. It's not correlating a lot with the experimental result that we are having from a real experiment. So we said, well, it's time to actually do some more tricky molecular dynamics, and we are going to do enhancing sampling methods. So basically, we're going to use metadynamics, free energy perturbation, Gaussian accelerated molecular dynamics, whatever you think is fitted for the task. And after a lot of work and pain and CPU hours, we have some binding of free energy that is also less than 1.4 kilocalmole, usually, if it is running correctly. This value is really, really good, and it can be achieved by just a normal force field, and we are almost at the precision of an experimental value, so things are getting blurry right now with the experiment and the result from a real computational chemist output. And somebody would just come back to us and say, well, I don't like equilibrium simulation, I just want to do non-equilibrium simulation. And then we can get some K in, K off. That is also a really, really tricky values to get. So just showing this that computational chemistry, computational physics is a field that has been around for a lot of times. A lot of the problems were kind of solved in some way, and there are a lot of things that machine learning can actually do to improve this kind of result without actually changing the field completely. And as you also see, as soon as we go for better precision for a new type of results that can correlate to our experimental value, we're also increasing by a lot the CPU time. And sometimes the parallel difficult word for me, you cannot do the parallel simulation, basically. Free energy perturbations, yes, but metadynamics, not really. And when something gets really expensive, we kind of get excited because it's an expensive calculation. So I can see some active learning inside. So basically, now we are basically back to E2lead phase. And this is one of the main topic of the work, is basically building an active learning cycle for docking as an oracle. So imagine that you are running a campaign from a really, really big data set, and I mean real level of data set. You cannot, even if docking is a high throughput method, you cannot actually dock every compound inside your protein. So what do? You basically decide, well, I can dock just a random percent at the beginning. I can train a model to actually predict my binding score. It's a really bad score. We can probably correlate on that. And then we can predict the rest. It's going to be cheaper than actually run the docking simulation to every compound in the data set. And so you select your next compound with your objective function, be that certainty, if you want to minimize the free energy, or if you want to actually go away from a compound or a scaffold that you know that are patent, you can do that. It's an objective optimization at this point. So you start to run this loop and you start to improving. And at the point, your really, really, really big data set is going to be a decently sized data set. At this point, you're going to say, well, I want an expensive and even more expensive calculation. I need to actually understand if it is the binding free energy in a precise way. So on your compound dataset, instead of your hammer, you're going to start to utilize some kind of free energy perturbation techniques, some metadynamics, some enhanced sampling that is really more expensive, but it's active learning, so it's an expensive oracle. We're fine with that. So I'm gonna do free energy perturbation with some compound. I'm gonna train my surrogate model to actually predict the absolute binding free energy, and I'm gonna label the big data set and so on, so on, so on. We're gonna have some new compounds to test. But we discovered with this kind of way, this kind of loop, that doing this is absolutely expensive. Absolute binding free energy is relate to different kind of compounds that are really different and things like that. But in a real drug discovery scenario, you're gonna probably use something more cheaper. And in this kind of case, the question is, can we make it faster? So we're gonna do free energy perturbation on relative binding free energy. The loop is basically the same. This is basically done everywhere, most likely. Schrodinger, I think FA plus actually have this kind of functionality. So active learning with free energy perturbation is something that the industry is currently behind and is actually doing. But you train your model, you do your relative binding free energy calculation, and you get to a point where you're basically doing lead optimization with a really precise techniques. And at this point, I basically talks a lot on docking, free energy perturbation, a little bit the active learning cycle, and just telling you check the PDB. But we did not even talk about the machine learning model that we can utilize. So yesterday you had an entire day basically going with the fundamental on how we can embed featurize molecules from smile graphs and so on, so on, so on. But that's what they are. They're molecule in vacuum, and now we have molecules that are in protein, probably docked inside, and we're trying to actually leverage this information to predict something and predict it in a better way. So instead of using fingerprints, we can do what usually called 3D-based featurization or descriptors. So basically, instead of representing your molecule as a graph with bond, you basically have atom in space, and you're basically just embedding in some kind of way the atoms without any bond inside a spherical cutoff that you decide. And this opens a lot of problems. Like you need to just from the first problem is that you have a spherical cutoff. Like how can you select something if you have an interaction that is way longer than it's a long range and your cutoff is basically just not picking it? That's a problem that is basically going on in the field. But basically, you're just transcribe it as information that is spatially into an undimensional descriptor that you can use as a normal feature of your system. And this have been going on for quite a while from the physical descriptor. So atom center symmetric function Ani2X is based on this kind of descriptors. It's just a Bell and perennial neural network trained on this kind of feature. Then you have the smooth overlap of atomic position as SOP from the Gabellini group, and it's used a lot in material science. And also atomic cluster expansion that is usually called ACE. You heard a lot about MACE today, and this kind of theory that actually been given birth from to the atomic cluster expansion is the one that is currently used in MACE. The only difference that physical descriptors are not trainable, and now we are in a kind of new area of this kind of featurization for material science and biological purposes, where this kind of featurization are trainable because they are just embedding from a neural network or a graph neural network. So all the part that we talked yesterday and a little bit today about equivalent is getting really complex in this kind of field, and so hopefully getting a way better result in the future and right now. So I don't know, I'm in the time, so because I technically did finish. So we're gonna have the 30 minutes break if we don't have a question.
Anyone have any questions for Cristian? Oh, I see one in the front. I'm coming.
More question means less break, by the way.
Thanks again for the talk. I had a question about one of the filters on your earlier slides. You had one about a drug likeness filter.
Oh,
I'm
okay.
just wondering what that means and whether there's a reason that has to be applied at the later stages and not initially when you're like looking at the, let's say the enam and real data sets, like, like by default or just
Not really. Just honestly put it there. It's mostly like after you did already your screening with your machine learning model, and you just screen again. It's just applying a medchem filter. Probably you can just check the QAD descriptor as how much value do you want. It's just an empirical correction in this kind of case.
Sorry, so drug likeness, does that have to do with something like synthesizability or?
No, it's in this kind of field. I will say that you can in this kind of step you can use a lot of different type of filters. Dark likeness can be just a QAD descriptor for that you can calculate from RDK. It is basically telling how much resemble do you have on a real drug. That is basically not really that useful description of your molecule. But you can go crazy in this kind of step, and if you connect and talking about scientists, I cannot say the word. Making the drugs something that is really important, and you will probably need to have a talk on what kind of molecule you're proposing by how easy they are to make, because sometimes it's just you're proposing a really good molecule, but somebody like you cannot make that. So back to step one at this point.
Thank you.
Okay, I see a question in the very, very back.
Hi, thank you for the presentation. In one of the slides, you use, you talk briefly about AL, and I was wondering, first, why do you think it's so like present whenever people usually talk about drug discovery, and which type of acquisition function or acquisition functions did you use for your batch acquisition?
So basically, they're using drug discovery mostly because not a lot in the docking. You can use that if you need to screen down a really big data set, but on lead optimization, still you need to do a lot of simulation that are really expensive, and you don't probably most likely you need a way to actually proxy your solution, and that's why actually learning is a good way to do this. And as an acquisition function, usually you always try to do some expected improvement probably on the binding free energy, but in the loop, here that is basically the lead optimization loop where you run free energy perturbation and you train the model. Usually you can go. It depends on the case. There are some times where you are developing from a scaffold, so you want to basically move away from your chemical spaces. So there is a little bit of tricks inside that you probably need to take care of. So it depends, I guess.
Okay, last question.
So this is a little bit about the training dynamics. When you finish to perform a batch acquisition, do you, as usual, we do like in AL, we train from scratch, or do you just retrain the models on the newly acquired data?
Usually, I will retrain on the newly acquired data.
Only, or on the initial training?
No, it's you basically build the new data set with all the data that you've labeled in this expensive way. So you retrain on everything.
No, it's not clear.
So are we talking about retraining like something a Gaussian process, or fine-tuning a model on the new data?
So when you perform the batch acquisition, you start with some initial data set, right? Assume that's what the compounds data set is. And then you perform within the AL loop, you perform some batch acquisition, right? Then so the question here is, do you add the newly acquired batch to your compound, assuming that maybe you select like the top base top K, for instance, from the whatever you sampled from, and do you retrain from the scratch on the data set that was compound data set union the newly batch acquired, or only on the batch that you acquired at that specific round?
I understood. You retrain on the entire one. So not only the new batch that you acquire, but the entire data set. So you basically add your new batches to the old one, and so on, so on, so on.
Okay, did you try? Know that usually we retrain on the whole like union set, but did you try just on the newly one to see if it brings like any improvement or like difference in performance?
No, I didn't try.
Okay, thank you.
That sounds like a great discussion that you can have during the break, which we're going to head to now. Thank you, Cristian. We'll head out for the 30-minute afternoon break, and please be back here at 3:30.
Cristian will put the link to the collab and the GitHub right now. So if you want to set up your environment during the break, please follow it.